Thank you very much for having me. It's a great pleasure to participate in the NNI workshop. In the next 10 minutes, I will reflect on nanoscience and nanotechnology at IBM Research. I will present a few examples of research activities we pursue in the area of nanoscience and nanotechnology, and will highlight what I think the opportunities may be in the future. As you can imagine, nanoscience and nanotechnology is really in the DNA of us. About 40 years ago, many may remember, my dear colleagues Gerd Binnig and Heine Rohrer invented the scanning tunneling microscope. This was really a breakthrough tool. For the first time, nano was made visible. Single atoms could be visualized. And in the due course since then, we learned to manipulate individual atoms. We learned to build atomic structures from the single atom up. This tool significantly boosted the scientific discovery in nanotechnology. And only 5 years later, again, Gerd Binnig, together with her colleague Christoph Gerber and Professor Quaid from University of Stanford, have invented the atomic force microscope, another breakthrough tool, a really very versatile tool where a lot of inventions also have made. It has been improved over the years, and with this tool, with the AFM, we can now make visible magnetic properties, temperature distributions at the nanoscale, and we can even use it for nanolithography and much more. So nanotechnology, nanoscience is key. It's really at our DNA, and we have opened the door to this area. In the research which we pursue in this field, we are pushing the limits of what we can understand, what we can build, and what we can measure. Because it's so important, nanotechnology and nanoscience, understanding the physical mechanism, the chemical mechanism, and this is as important and critical as ever before. So let me give you an example. This is the example of silicon transistors, state-of-the-art silicon transistors as we use them today in our devices. We are working on the new technologies, new transistor technology for the 5 nanometer and beyond. These are so-called gate-all-around nanosheet transistors. You see here an example of a publication of my colleague at the VLSI 2017 conference. In this picture, you see a cross-section of the nanotransistors through the nanosheets. These nanosheets represent the silicon transistor channel. There are 3 of those nanosheets stacked on top of each other. They have a thickness of 5 nanometer, and they really provide, due to the gate-all-around shape, a superior electrostatics and dynamic performance compared to extremely scaled FinFETs. If you look at the bottom picture, you see 3 years later, just published last year at the IBM, the nanosheet FET update. And you see a sophistication of the material stack which is used in these nanosheets. At the core, there's again a silicon core, but then you have a 1 to 4 nanometer silicon germanium layer. This is covered homogeneously by a 1 nanometer silicon cap, and on top of this, the Heike dielectric material and the metal gate is deposited. The silicon germanium has a certain composition and is compressively strained. This strain leads to band engineering and thus to a 100% uplift in peak hole mobility. The channel resistance is reduced by about 40%. This example shows that a better understanding, a better control of dimension, interfaces, strain, and much more is needed in order to further improve the device characteristics, also in the future. At the IBM last December, much more has been demonstrated, many more devices, all using nanotechnology, nanomaterials. And you see here some of them. They are used for applications not only in CMOSFETs, but also for memory devices, for nanophotonics, nano interconnects, RF devices, biosensors, and also more and more for quantum devices. Nanomaterials are key. They lead to emerging nano devices. And over many years, many new materials platforms have been developed. For example, nanowires. We have been actively working in this research field starting in 2005, first developed and investigated silicon nanowires, and then later on moving to 3-5 nanowires and nanostructures directly integrated on the silicon platform. We have perfected the material deposition, the material properties, investigating them for electrical, optical, electro-optical, and different applications. You see here examples like MOSFETs, tunnel FETs, steep slope devices, but also photodetectors or photonic crystal cavities where the 3-5 material in these nanostructures is directly grown in the crystal. Now we are also looking into using these materials for quantum devices. So a lot of activity is going on in that field. If you look at the carbon nanotubes, we have been pushing the limits of this device technology for MOSFETs. The shortest gate length carbon nanotube MOSFETs were 9 nanometer, which we've demonstrated without showing any short channel effects. Contact resistances have been reduced by using end bonded contacts, where the metal atom is directly covalently bonded to the carbon atom in the carbon nanotube. More is going on in 2D materials, where also a lot of research has been going on to perfectionize the materials, to engineer the materials. There's a plethora and a variety of different materials available, single sheets, double sheets, stacked heterostructures, etc., which can be used for different applications. More research and development is, of course, also needed in this field. I would like to highlight a recent example where IMEC has demonstrated at IBM last month that there is already a integration process flow on 300 millimeters to produce double-gated tungsten sulfide FETs. For the nanotechnology, it's not only important to develop the materials and develop new devices, but also to understand the physical phenomena at the nanoscale. And therefore, we also need to always push the limits of characterization in order to gain insights into the physical mechanisms. Here, I would like to give you an example, which was kind of a byproduct of a memory project of the Millipede project, where we investigated and built heatable AFM tips. This technique is the so-called scanning thermal microscopy, where we use a heatable AFM tip in order to sense the temperature distribution at the nanoscale on a surface. We can do this nanoscale thermometry quantitatively and can measure the temperature distribution with a spatial resolution of below 10 nanometer and a temperature resolution of below 1 millikelvin. This technique can be applied to many different areas. We used it to identify hotspots in resistive RAM devices to indicate the filament. In vanadium oxide phase change switches, also here hotspots can be evaluated. In nanowire devices under operation, we can measure thermal resistances. We can identify contact problems. We can measure the Peltier cooling and the Joule heating at the same time. Or another example is here on the right-hand side, where we look into polytype indium arsenide nanowires and can identify the thermal properties of the zinc blend and the Wurtzite segments and their differences. This is just an example, and more insights can be gained using this technique. These techniques are very important, and we actually drive them from the basic research to the commercialization. But we are not commercializing them, so we also often work with partners to do this. AFM for nanoprobe lithography is another example I would like to give you. In this case, we use this heatable tip to actually nanostructure 2D and 3D patternings. We use a polymer thin layer where we can use the heatable tip to evaporate locally the polymer film and thus create a nanostructure with nanometer resolution, which we can transfer into a hard mask and from there into a thin film below. This technique can not only be used for 2D patterns, but also for three-dimensional grayscale patterning as shown here. These are two examples where we, for example, showed Richard Feynman as a grayscale picture. You see here the size bar of 1 micrometer. And we also have demonstrated a famous Swiss mountain, the Matterhorn, as a grayscale image with a height resolution of 1 nanometer. This technique actually has been commercialized by a PhD student and a colleague who founded a company in 2013 called Swiss Litho. They established a commercial tool, NanoFraser, which is the first hybrid mix and match nanolithography tool, and it works in ambient. Later on, this company was integrated into Heidelberg Instruments, and today you can actually buy a commercial tool which allows you to pattern 200 millimeter silicon wafers with this technique. So toward the end, I would like to highlight that we are not at the end with nanoscale technology and nanoscience. There is much more to come. It's critical and important as ever, because we need to gain further insights and understanding at the nanoscale and to drive forward new materials and also new devices. We need to understand the physical and chemical processes for the various device applications in areas as indicated below. Whether these are electronic devices or photonic devices, nanosensors, also for biological applications or health applications, or also quantum devices. We need to perfect the engineering of nanostructures and devices. In particular for quantum devices, where an individual spin is important, where a charge somewhere is important, we need to locate each atom precisely and with methods which are feasible for mass manufacturing. To explore, understand, and utilize new phenomena is key. For example, topological effects. These are super interesting and can be applied to many different applications again. Controlling the nanoscale composition and structure is key for them. So with this, I think it's really important that research in nanoscience and nanotechnology is critical and important as ever. Thank you very much.